Well friends, from today onwards we take up an altogether new phase of discussion, the control system design, wherein we cash on the background we have established, the background on the various type of controllers, the background on the commonly used hardware and all other aspects of the subject we have discussed. Now when I say control system design, please see that it's a very big umbrella. Under the design, the selection of the plant is also a very important attribute. The selection of sensors for the system is also an important factor, and so many other decisions you have to take as far as the total design of the system is concerned. The decisions which are based on many a times, in addition to performance requirements, decisions are based on economic and other considerations as well. But when I say that what we are going to discuss in design, I think let me make it very clear. I assume that all other decisions have already been taken, because the considerations are so widely different that in a classroom discussion we cannot capture those considerations. The considerations about the plant, the considerations about the sensor, the considerations about the controller, the type of controller, the structure of the controller is also decided. Okay? A design simply will mean for me actually a compensator design. What is a compensator? Compensator is that component of the total control system which is going to compensate for the deficiency in the plant. If this particular DS was not there in the picture, then also it's a complete control system with the plant and the sensor and a feedback loop. But that complete control system, if it satisfies your requirements, naturally you don't need any compensation. But if it does not satisfy your requirements, then you need a compensation, and you will add a suitable compensator, a hardware device which is going to compensate for the deficiency in the performance. Okay? So the design in this classroom is primarily focused on the design of the compensator and not the design of the overall system. I am sure I have given enough background on the problems associated with sensors, the problems associated with plant, the error detectors and all other factors which make up a control system. The background which we have established, I am sure, will help you in taking a decision when you take up a true industrial application for design. Okay? So in the limited time, the discussion may primarily be focused on the compensator design. The word compensation, the word compensator now onwards should be clear that it's a piece of hardware which you are interfacing to the plant which already has been decided. You see that? I assume that the change in GS, the change in HS is now not possible once you have taken a decision on certain considerations. The only change you can do is that in DS, because that change first of all is easy and secondly is not very costly. After all, what will be this DS, or what is the change required? A little change in the op-amp circuit. DS will consist of an op-amp circuit, or it will consist of software in a digital computer. So a change in DS requirement will mean that changing the software or changing the op-amp circuit which constitutes the controller. So the only change required in this aspect, DS only. Okay? And we are going to take up as to how a suitable DS can be selected so that all our performance requirements can be satisfied. Okay? And I first of all take up a technique called the root locus method. Qualitatively we know what performance do we want, and now quantitatively we have to design a DS so that that particular performance is achieved. You recall the performance. Our performance is in terms of TR, TP, zeta, omega n, MP, settling time, steady state error and so on. These are the performance measures, and we have seen that many of these performance measures are conflicting, but there are two important points, two important parameters, zeta and omega n, which give you completely the transient performance of the system. And these zeta and omega n, you know that can be translated into the desired locations for closed loop poles. So can I say that actually the total performance which I have given you in terms of all these measures, as far as the transient part is concerned, Steady state part is separate. As far as the transient part is concerned, this transient part can appropriately be translated into a pair of dominant closed loop poles. So, if you have a large order system, if you have a system higher than second order, in that particular case you have to see that all other poles should become insignificant, so that these zeta and omega n have got the meaning in terms of peak overshoot and settling time. So, this aspect we will see in our design examples. Given any of these attributes, you can take into account these attributes suitably, so that the performance can be translated into a pair of complex conjugate poles. And now I say that whether your performance is satisfied or not, it is more appropriate to see in terms of a root locus plot than any other method. And what is a root locus plot? That I will like to exemplify first through a simple example. Let me take a very simple example. K over S plus 1 into S plus 2 is my plant, and K is one of the parameters which is subject to change, maybe an amplifier gain. Now, as far as the closed loop poles of the system are concerned, you know that closed loop poles of the system are the roots of the characteristic equation. Let me write the closed loop transfer function as K over S squared plus 3S plus K plus 2 plus K. Yes, this is the closed loop transfer function, and therefore closed loop poles are S12 minus 3 by 2 plus minus 1 by 2 1 minus K under root. Please check whether this is okay. 1 minus 4K under root, probably 9 minus, that is right. Please check if there is an error, do tell me immediately. So, these are the closed loop poles of the system, minus 3 by 2 plus minus half 1 minus 4K under root. Now, let us see how does the system behave as the value of K changes from 0 to infinity. After all, this is the total change which you can make. S12, let me rewrite this equation as minus 3 by 2 plus minus half 1 minus 4K under root. Please help me here. Give me the locations of the poles as K varies. What happens when K is equal to 0, please? What happens when K is equal to 0? In that particular case, you find that the closed loop poles are same as the open loop poles of the system. I am sorry, let me make a fresh sheet. S12 minus 3 by 2 plus minus half 1 minus 4K, and your open loop transfer function is K over S plus 1 into S plus 2. Help me get started with K is equal to 0. So, K is equal to 0 means you find one of the poles is at minus 1 and the other is at minus 2. So, I make a point here as minus 1 and another point here as minus 2, and let me write K as a running parameter. K is equal to 0 at these 2 points. These are the closed loop poles. Now, increase the value of K. Increasing the value of K, you can easily check, please, the poles will be at this particular location for a slight increase in the value of K. Help me, what will happen if I make K is equal to 1 by 4? If I make K is equal to 1 by 4, I get the poles at minus 1.5 repeated and real. At K is equal to 1 by 4, the two poles are repeated and real, and they are located at this particular point. So, you please note what is happening in terms of a locus. If K is increasing, one of the roots is moving this way, I can make an arrow here. You can check this by simple calculation, this being a simple quadratic. I need your attention at this particular point, please. One of the closed loop poles is moving on this line as K is increasing from 0 onwards, and I reach the value 1 by 4. Another root is moving on this line as K is increasing from 0 and reaches the value 1 by 4, and these two roots meet at a common point where the root is minus 1.5 and the value of K is 1 by 4. Okay, help me please. If I increase K further, what will happen? What will happen to the roots if I increase K further? The roots become complex conjugate, and you can easily establish this being a quadratic. The roots always lie on this line because the real part is always minus 1.5. the roots have to lie on this vertical line, the real part being always minus 1.5. Only this part changes and this part now becomes a complex part for k becoming greater than 1.4. So it means I can visualize it this way. Please see that as if one of the roots is moving from this point at which the root was minus 2, as k is increasing, one of the roots is going this way and maybe it goes this way, and the other root, you start from this point, it moves this way and maybe it then goes this way. It does not matter at all whether you trace your root locus this way, that this root goes this way, the other this way, or the opposite, because it really does not matter, because after all you are interested in two closed loop poles. Whatever way you track, you see the two closed loop poles will remain the same. So it is really not significant whether you call this as one branch and this as the other, or you make it the opposite way. So what I want to say is that there are two branches of the root locus. Which root? The root of the characteristic equation or the locus of the closed loop pole of the system. One of the closed loop poles will always lie on this particular locus from this point to this point, and the other closed loop pole will always lie on this particular locus as k is varied from 0 to infinity. So what I want to say is this, that whatever information you wanted to have about a system in terms of rise time, settling time, peak overshoot, zeta, omega n, I want to say that this is clearly visible in this form in the root locus plot. And how? First of all, you see, from the root locus plot it is very clear that for any value of k from 0 to infinity, the system will never become unstable, because the closed loop pole will never cross the j omega axis. See the conclusions. This is a very simple situation. In complex situation also, we will be able to make conclusions about the system very quickly and easily from the root locus plot. What I say is that a root locus plot is a complete description of the system in terms of variation of one parameter of the system, which is your design parameter. So once the complete description of the system with respect to the design parameter is known to you, you simply translate your requirement, performance requirement, and get the value of the design parameter. That is going to be the root locus method. So you see that there will be two steps in the root locus method. You consider what is your design parameter. It may be the derivative constant of a PD controller, it may be an integral constant of a PI controller, it may be an amplifier gain, or it may be any other thing. You at this juncture you assume as if there is only one parameter. There may be more than one parameters as well, but start with only one parameter. So what you do is you plot the root locus diagram with respect to that parameter as it varies from 0 to infinity. So it means the total behavior of the system with respect to that parameter is visible to you in terms of the root locus sketch, and then you can translate your requirements and look at the root locus sketch to find out what should be the appropriate value of that parameter. These points will become very clear later, but at this juncture it should be very clear to you that a root locus plot is a complete description of the system with respect to a specific parameter of design. So in this case k, you find, for example, if you take this point, you know that the roots are complex conjugate. So if you take larger value of k, what will happen? You know that the system damping will increase or decrease. Tell me, if I increase the value of from this point to this point, if I go, what will happen to system damping, please? It will decrease and increase, both terms are coming. Please see that it will decrease. This system damping is given by this is theta, cos zeta is equal to cos theta. You can check that this point also, as the roots are going this way, we are coming from the situation of over damped to critical damped and to under damped, and as you go this way, as k increases, the system damping will decrease. This you can easily check. So you see that the effect of k, system will never become unstable, system damping will decrease with the value of k, up to k is equal to 1/4, the system is critically damped or over damped. All these conclusions can easily be made from the root locus sketch. Okay? Questions welcome, please, at any stage. Come on, make a little change in your diagram. I now say that your system becomes k over S into S plus 1 into S plus 2. This is your open loop system. What is the difference now with respect to the earlier diagram? You will note that the difference is this, that the plant now has an integrator. The plant has an integrator. What is the characteristic equation of the system? It is a third order characteristic equation as a function of k. Though I do not claim that you can immediately get the roots analytically. Assuming that for different values of k from 0 to infinity you have got the roots. How will the root locus diagram look like? And suppose you have got the roots, whether the complete information is available or not, let us say. The open loop poles are at S is equal to 0, at minus 1, at minus 2. I leave this as an exercise to you. Of course, you need not do it on the computer. I am going to give you the methods how to make a root locus sketch. But the root locus, as I know, will be of this nature. Please see, these are the root locus branches. This is the total root locus diagram. You can imagine that you will write the characteristic equation of the system, vary k from 0 to infinity, get the roots and plot them and join them by a line. If you do this exercise, the red lines will come. Okay? At this point, I hope you won't mind accepting this statement. Now let us see the conclusion. The conclusion is very visible from here. Look, this is the point at which k is equal to 0. This is the point at which k is equal to 0, and here is the point corresponding to k is equal to 0. You are at the open loop pole points at k is equal to 0. Increase the value of k. If you increase, one root will go this way, other root will go this way, third root will go this way. These are the three branches. One branch going like this way, this way. The other branch going like this way, and the third is here. So for any value of k, you are going to get three roots from the root locus plot. Increase k further, you are reaching this particular point where the two roots are repeated and real, and let us say the third root is here. Further increase in k gives you complex conjugate roots. Okay? Now you see that this system clearly shows, as you are increasing the value of k, you are drifting towards the imaginary axis, and your system is becoming more and more, the system is going more and more towards oscillations and instability. And the third root tells you, please see, the third root also gives you the location. You can test the dominance condition and see whether the contribution of the third root on the dynamics of the system is going to be significant or not. If this particular third root is about 4 to 5 times away compared to the real part of these complex conjugate roots, in that particular case, the effect of this particular third root on the dynamics of the system is going to be negligible. Increase your k further, you are coming at this particular point, and you are going closer to the imaginary axis. At this particular point, there is some value of k which makes the system oscillatory. You further go and increase the value of k, your system has become unstable. So you will find in this particular case that this point you are getting as k tends to infinity. This point is going to infinity as k tends to infinity, and here is a point which goes to infinity as k tends to infinity. The only point I have left to you is that you compute it on computer and make this as the sketch. So can we say that this particular diagram has got three branches? One branch is, arrow is shown like this, from k is equal to 0 to infinity, k is a running parameter. The other branch, k is equal to 0 to infinity, k is a running parameter. The third branch, k is equal to 0 to infinity, with this as the third branch. As I told you, really scanning this way or this way is immaterial, because the two roots are going to be complex conjugate and symmetrical. So you just see that if you have a root locus diagram, the effect of parameter k is totally visible from the root locus diagram. This is what is going to we are going to do with the help of the so called root locus technique. Everything about the system is visible. Routh stability criterion did give you the range. You see that the information that from k is equal to 0 to k is equal to this point, the system is stable, and k is equal to this point to k is equal to infinity, the system is unstable. This information is available to you from Routh stability criterion as well. But it really does not give you the system poles in that particular region, while the root locus plot gives you the system poles in that particular region. That is important. Okay, you can at this point say that what is a root locus method after all? If I have the characteristic equation, I can sit on the computer terminal and get the poles for any value of k I am interested in. My argument is same as I gave you in connection with the route stability criterion. There only numerical values will be available to you. You will definitely need this type of sketch to see how the parameter is going to affect the closed loop poles. So, those numerical values are also required to be plotted. So, I do not say that the computer is not useful in root locus method. The use of the computer is only to the extent of getting this plot. Once this plot is available, you have to apply your own judgment to see that what should be the value of the parameter k which satisfies your performance requirements. Okay? Yes, please.
The third root does not affect the transient performance, the one which starts from -2 and goes to infinity.
Why?
So does it affect the transient performance in like when you are deciding the design of the system?
Yes, this we have discussed that the third root of a system, if it lies in the insignificant range, then it does not affect the transient. In this particular case, for example, if the numerical values I have not given you the numerical values, but because at this particular point, what is the value when the roots are there? You see, when I take complex conjugate roots, this is the real part. Let us say it is -0.5, and let us say this is -3. Yes, it will not affect. But so it means the root locus plot will give you that information as well. You cannot say, you cannot conclude that the third root does not affect the transient performance. Let me take a situation where this 0 is close to this.
That's okay. In this particular case.
In this particular case, it depends. But I want to say, in general, you have to determine the third root and check the dominance condition. If it does not, in that particular case, your performance translated into these two poles is the acceptable performance. And if it really affects, then the performance you have translated in terms of these two poles is not the true performance, and you have to suitably account for this effect as well. Okay? I hope it is clear that the third root is also given by third or any number. In a higher order system, it will be more than 3. So, those roots other than the dominant roots also have to be investigated and the dominance conditions to be examined. So, if it is satisfied, you are happy. If not, then you have to suitably re-enter the design cycle so that the effect of the other roots other than the dominant roots is accounted for. Okay? Fine. Let me take one more example. Say k over s plus, let me take it at 5 divided by s plus 1 into s plus 2. You know that what is this? This now has a 0 which is equivalent to adding a PD controller to the system. You see, with the background, now you see mostly I will be working with transfer functions to save time. Hardware I cannot bring in. But any transfer function should immediately give you a corresponding system, you see, in your mind, so that you can visualize that system in your mind. This is a type 0 system with a PD controller. For example, a typical system could be like this. It could represent other situations as well, but one typical situation could be a type 0 system with a PD controller. A type 0 system could be a temperature system or a liquid level system or any other system you can think of. Now, let us see what is the root locus sketch of this. Let me make it here itself, though there is an overlap. But since these poles and zeros will be available to me here, so I make a sketch here itself. S is equal to -1, -2 and a 0 at -5. Please see, zeros I will represent by a circle. It is not to scale, or let me make it a little more appropriate. If not exactly a 2 scale, it should make some sense. -1, -2, -5. 0 by a circle. So, this is the situation. Now, I again tell you that get me the characteristic equation. K is a running parameter, and with respect to K, the system should be characteristic equation should be investigated. So, in this particular case, if you do that, what you get is the following. Please see, this is what you will get as the root locus sketch when you vary k from 0 to infinity. Let us see how does it come up for various values of k. K is equal to 0 here, k is equal to 0 here. Two poles are there, closed open loop poles. You start with this. There are 2 branches, please see. Only 2 branches, because for a second order system there cannot be more than 2 closed loop poles, and hence there cannot be more than 2 root locus branches. By now you must have understood every root locus branch corresponds to one closed loop pole or one root of the characteristic equation. Come on, help me please. What do you visualize? You start from k is equal to 0. So naturally you are going this way. You increase your value of k, you are going this way. At some value of k, your roots are repeated. Increase the value of k further, you are going this way. That is, the roots are becoming complex conjugate. That we will see. At this juncture, don't worry, this see about the general, I am going to give this information also. But at this point you just see the general shape, assuming as if this may not be a circle even, okay, though it is a circle no doubt, but let us say that it is not even a circle, it is any shape. Concentrate on the aspect of how this particular system is going to convey the information about the transient performance of the system. These are the branches. Now you see that the two roots meet again on the real axis. It means there is again a value of k for which the roots are real and repeated. Increase the value of k further, one of the roots goes this way, the other root goes this way. At this particular point k is equal to infinity, and at infinity k is equal to infinity. These arguments, why at this particular point k is equal to infinity, please at this moment don't worry about this. This is coming in the sequel. You see, I am going to prove all these things to you. But at this point you just see that if this is the root locus sketch available to you, it nicely tells you what is the effect of the parameter k on the system performance. You find that because of the 0 you have added now to the system, you see not only that the system is stable, the system is relatively more stable because your vertical line has been pulled onto the left hand side. You see this point please. Without the 0, you recall the root locus diagram, it was a vertical line. If you when you added an integrator, the vertical line was pulled towards the imaginary axis. So it means the integrator was making the system less stable. And when you have added a 0 into the system, say a PD controller, the vertical line has been pulled towards the left hand side. It means the system has become now more stable. One observation which we have made. And the second observation is this, that you see that after this value of k, the roots are complex conjugate and the real part of the roots is increasing. You know that if the real part of the imaginary part is not very appreciably increasing, please see that imaginary part from this point to this point, the effect is not that appreciable, but real part is increasing drastically. And you know that real part is zeta omega n, and you know that 4 by zeta omega n represents settling time. So it means larger the value of k, faster is your system as far as the settling time is concerned. Zeta omega n is the settling time and zeta omega n is increasing, as you see, okay, when you increase the value of k from here. So it means the system becomes faster, it settles down faster as the value of k is increases from the value from this repeated roots value, whereas it is critically damped, to the values where it becomes under damped. Okay. So this way the root locus plot gives me the picture about the total behavior of the system. So it means now if I have this sketch and all those TR, TS, TP, MP, etc. have been translated into two closed loop pole locations, in that particular case what is after all the design? The design simply will be this, that find out where is that closed loop pole locations. If these are the locations, find out the corresponding value of the parameter k, your parameter has been designed. In this particular case there is no third root, so there is no problem of dominance condition. Yes, one thing you will have to see in this parameter, you see the system 0 at s is equal to minus 5 is same as the closed loop 0. You can see this, or you can even say g over 1 plus g type of equation. The open loop 0 at s is equal to minus 5 is same as the closed loop 0 at s is equal to minus 5. So you have checked this, but you should see where is this 0 lying. If this 0 lies close to your pole locations, you have to account for the effect of the 0 appropriately. And you know that how to account for the effect of 0. This 0 is going to give you a peaking effect early. So in that particular case what you will do, please tell me whether you will pull your roots this way or this way to account for the effect of the 0. These are the closed loop poles. Which way you will like to pull? You see that you will like to pull this to this way so that zeta decrease, zeta should increase. You want to see the effect of this s is equal to minus phi. The s is equal to minus phi, if it is close to this particular point, it is going to give you more peaking phenomena, that is, it is going to give you pronounced peak. So, what is your design? You will like to design for a lesser value of zeta, for a larger value of zeta. I am sorry, I made a confusing statement. I repeat my statement again. You know that the effect of 0 is to give you an early peak and larger overshoot. I repeat my statement, it is going to give you an early peak and larger overshoot. So, it means you should design for a little larger value of zeta, so that the effect of the 0 makes it what you practically want, makes it what is acceptable to you, and larger value of zeta is the appropriate zeta line you have to take account of, and larger value of zeta is given by this line compared to this line. Okay. So, it means if earlier, if your root locations are here, you will prefer these two root locations if the effect of 0 is significant. I mean, did I take care of the confusion I made, you see? Is it all right, please? If this is the location, you will most appropriately design for these locations, so that the effect of 0 is taken care of. Yes, if there is any question on this or doubt in this, please do tell me. You can find that compared to these two, you just compare these two locations, this and this zeta is larger compared to this zeta. The zeta is becoming smaller and smaller when you go this way. Of course, you in this particular design, you can never get a zeta lower than this, the line which is tangential to this. You cannot get a value of zeta lower than this, that is the upper limit, that is the limit you get. Now, I am comparing this point to this point. If the effect of 0 is significant, then I will try to pull the desired poles a little this way, so that the peaking phenomena pulls the poles on the other side and the value of peak overshoot becomes acceptable to me. Is it okay, please? Okay? Yes, say it clearly. Yes, it is not coming, it means there is some doubt. If there is doubt, please do raise a question. Okay. Some green signal at least has come for me to go ahead. Now, you see that I take the complete situation Gs plus minus Hs. This is my Rs Ys, a complete general situation let me now take, and let me say how the root locus diagram is going to help me. How do I construct the root locus and how the root locus method is going to apply in a general case. You know that in this particular case the closed loop transfer function is Ys over Rs is equal to Gs over 1 plus GSHs. Okay. See that if I break my loop here, the transfer function between this output, you can say that is B, the feedback signal. The transfer function between B and R is GH. So, in the terminology, various terminologies have been used, a loop transfer function or an open loop transfer function. It should not confuse you, please see that I may be using these words loop transfer function or open loop transfer function for GSHs. So, it means I say that for this particular system, Gs into Hs is an open loop transfer function. The definition is coming from this particular reasoning, that if I break the loop over here, this is the output processed by the sensor. So, the transfer function between the output processed by the sensor and the input is Gs into Hs when the loop is broken. So, in that particular case, this transfer function may be referred to as the open loop transfer function. For a unity feedback system, you can very easily see that the open loop transfer function is same as the forward path transfer function, because Gs is the forward path transfer function, that will become open loop transfer function as well. Okay. So, I see that the characteristic equation of this system becomes 1 plus GSHs equal to 0, where Gs into Hs is the open loop transfer function, and I am interested in the roots of this equation, because the roots of this equation I know are nothing but the closed loop poles of the system, and they are going to give me the transient behavior of the system. Now, in whatever form the open loop transfer function may be given to you, it is always possible to bring it in this form, k pi I equal to 1 to m s plus zi over pi j equal to 1 to n s plus pj. Always please see, after all this is a polynomial divided by a polynomial. Factorize the two polynomials, one constant will come out because these are s and s. So if you are taking s here and not a coefficient here, a factor will definitely come out. Okay, so that factor is k, and therefore any form of gs hs may be given to you. It is always to put that in this particular form, and this form k is the gain of the transfer function, zi's are the open loop zeros, and pj's are the open loop poles of the transfer function gs hs. Okay, any form it may. This form is more convenient as far as the root locus sketch is concerned, and therefore I make a sketch with respect to this particular form. Okay, zi's and pj's will be positive values if these poles and zeros lie in the left half plane, and normally they lie in the left half plane, though right half plane possibility is not ruled out. Okay, as I said that the zeros could be in the right half plane and the poles here also could be in the right half plane, because after all your open loop system can be unstable and the closed loop will make it stable. The only thing the point I want to mention over here, your closed loop poles cannot be in the right half plane, but your open loop poles can definitely be in the right half plane. Who prevents it? After all, your open loop system can be an unstable system. The purpose of designing the system is to design it to be a stable system. The closed loop poles cannot be in the right half plane, but the open loop pole can be. But mostly in most of the situations we will come across, the poles and zeros of the open loop transfer function will lie in the left half plane. Okay. So this total function, if you don't mind, I just name it by a single variable, single function, polynomial function fs. In that particular case, I can say that the characteristic equation of the system is given by 1 plus fs equal to 0. 1 plus fs equal to 0 is the characteristic equation of the system. And now the root locus method says that you look for, you see that you scan for the entire state space sigma j omega, entire state space you scan through and find out those points for which 1 plus fs is equal to 0. If you join those points, that becomes the root locus plot. This is the definition of the root locus plot. You have to scan through the entire entire S plane and join all those points appropriately, so that for a particular parameter which is varying from, let us say, 0 to infinity, if you find the roots of this particular equation, then that particular plot becomes the root locus plot. So equivalently, can I say that any point you take, let me take a typical point over here, this typical point will be a point on the root locus plot if at this particular point 1 plus fs is equal to 0, or equivalently, can I say, if at this particular point fs is equal to minus 1, or equivalently I can say fs magnitude equal to 1, and what is angle fs equal to, please help me, 180 degrees or a multiple of 180 degrees. The only thing is that it has to be an odd multiple for minus 1. So I am now putting it plus minus 2q plus 1 into 180 degrees, where q can be 0, 1, 2, 3, anything. See, I am just putting it in this form to take care of all possibilities, that is all. It has to be, it is minus 1, so it has to be an odd multiple of 180 degrees, that is all. That is the only point, and that is why I am putting it in this form, angle fs is equal to plus minus 2q plus 180 degrees. So it means any point here in the S plane is a point on the root locus plot if this satisfies these two considerations. One is the magnitude of fs is equal to 1, and the other angle of fs at this particular point is equal to a odd multiple of 180 degrees. Okay. So let me put this in a more appropriate form. Fs now has been taken as a parameter k, pi I equal to 1 to m s minus s plus zi divided by pi j equal to 1 to n s plus pj. I need your help, please. What is the magnitude criterion? The magnitude criterion will demand that k of course is a scalar constant. I am assuming k is greater than equal to 0 less than infinity. This is a positive parameter I am assuming, so it is a scalar constant. So, k pi I equal to 1 to m s plus z I magnitude. After all, the magnitude, the modulus can be taken inside, divided by pi j equal to 1 to n s plus p j magnitude should be equal to 1. This is one condition, and I call this as magnitude criterion or magnitude condition, you may call it. What is the angle condition? Please tell me. From here, the angle condition will be angle of s plus zi, summation of I is equal to 1 to m minus angle summation j is equal to 1 to n s plus p j is equal to plus minus 2q plus 1 into 180. This is your angle condition, please. Okay, you can see that. I think the summation point should be clear because the angles are added, and this negative sign also should be clear. So, these are the two conditions. One is called the magnitude condition and the other is called the angle condition. So, any point which satisfies these two conditions is a point on the root locus plot. If this is clear to you, then you have to answer my questions, please. You just keep the two conditions in mind, the magnitude condition and the angle condition. My question to you is this, that you scan through the entire S plane and tell me for what points on the S plane is the magnitude condition satisfied. If at all this question has an answer, do answer this question, or you say it is a vague question. My question is this, that at what points on the S plane is the magnitude condition satisfied? It is a general condition. Circle was a specific structure of poles and zeros. At what points in the S plane is the magnitude condition is satisfied? But okay, I give you some feeling about this. Let me take up the same example I had taken so that the magnitude and angle conditions become clear. I take the example of k over s into s plus 1 into s plus 2. Okay, what is this function? This is your fs function. I will come back to my question, please. I definitely need the answer to my question from you only. Just little hint I am giving by taking this particular example. Fs is equal to k over s into s plus 1 into s plus 2 we have already taken. Now you see that the magnitude condition is k divided by s magnitude s plus 1 magnitude s plus 2 magnitude equal to 1. Help me, what is the angle condition? The angle condition in this particular case is minus angle s minus angle s plus 1 minus angle s plus 2 equal to plus minus 2q plus 1 into 180 degrees. Is it all right, please? These are the magnitude and angle conditions. You know the root locus diagram, okay? Don't concentrate on that. Let me take a point and let me call this point as S naught. Help me, how do I check whether the magnitude condition is satisfied or not? This S naught has got a real part sigma and an imaginary part j omega. So what you do is, you in this particular case, you take this particular situation, k over sigma naught plus j omega naught magnitude, sigma naught plus j omega naught plus 1 magnitude, sigma naught plus j omega naught plus 2 magnitude is equal to 1. If this condition is satisfied for some k, you say that the magnitude condition is okay. This is because this point S naught equal to sigma naught plus j omega naught. So in the magnitude condition, you substitute your S is equal to S naught plus j omega naught, calculate the magnitude of this, calculate the magnitude of this, k divided by the multiplications of these magnitudes should be equal to 1. Okay? Please see equivalently, what is S? S is equal to 0 is this point. Please see sigma naught plus j omega naught magnitude if graphically visualized, is nothing but this distance on this particular plot. Okay. See the point, let us say -1. If you look at the point -1, then the point s plus 1 or s naught plus 1 is nothing but this distance visualized on the graph. And similarly, the third point at -2 is this particular distance visualized on the graph. So it means actually a magnitude condition will really not require testing these or calculating these magnitudes all the time. If you have a graph paper and you can read these red distances to scale by which you have taken these -1, -2. In that particular case, this k divided by this distance into this distance into this distance should be equal to 1 for the magnitude condition to be satisfied. Okay. How about the angle condition? Look at the angle condition. Angle at s naught. You see, again you can do your calculations using the calculator. You substitute your s is equal to sigma naught plus j omega naught. What is the angle? Angle is tangent inverse omega naught over sigma naught in general. But what is that in that particular case? What is this angle? This angle tangent inverse omega naught over sigma naught is actually nothing but this particular angle, and hence if you have a graph paper available, you need not do the calculations. You substitute your s is equal to sigma naught plus j omega naught. Angle s naught is equal to tangent inverse omega naught over sigma naught is same as this angle drawn by this blue line. This can easily be examined. Is it all right, please, this angle, or I am making an error? Please see that the angle contributed at this particular point is going to be equal to this. What is the angle? Omega naught. Omega naught is this and sigma naught is this. Okay. So at this particular point, if you are testing, what is the net angle contribution as far as this particular pole is concerned? Yes, this angle you calculate s plus 1, this angle you calculate. So these are the angles which are contributed this particular these particular factors. So if you take these angles, some of these angles with a negative sign, because these angles are in the denominator. Because these angles are in the denominator, so when they come in the numerator they will appear in the negative sign. So you have to see this particular angle, and the total angle the contribution at this particular point gives you the angle criterion. If this is satisfied, if both these conditions are satisfied, you will say that this point meets the magnitude and angle criterion and is therefore a point on the root locus plot. Okay. This is definitely a point on the root locus plot in that particular case, right. Now can I ask you my question? This was a very specific case. My question was general. You have fs equal to k pi I equal to 1 to m s plus zi over pi j equal to 1 to n s plus pj. What are the points at which the magnitude condition is satisfied? Yes.
The distance from the product of the distance from the open loop poles equals k times the product of the distance from the open loop zeros.
Yes. K is a variable from 0 to infinity. So my question is still not answered. What are the points on the S plane for which the magnitude criterion is satisfied? Yes. Well, say it loudly. Yes, it's all points in the S plane satisfy this requirement. You can just take, imagine this is very right answer. Please see, you consider any, after all your k is variable from 0 to infinity. Though now it may look like a trivial question to you. You see that you take any pole 0 combination, you take. So if you take any pole 0 combination and take any point in the S plane, okay, you take the magnitude of k equal to inverse of that magnitude, the magnitude criterion is satisfied. So you see that the magnitude criterion is always satisfied for any point on the S plane, but it does not mean that any point on the S plane is a point on the root locus. because it is both the magnitude and angle criterion which are to be satisfied. Can we make a similar statement on the angle criterion, that all the points satisfy the angle criterion? Please see, the answer will be no. So it means now my procedure of making this sketch, the root locus sketch, is going to be the following: that you only concentrate on the angle criterion and scan the entire root locus plot, scan the entire S plane and make all those points or connect all those points at which the angle criterion is satisfied. So all those points are definitely points on the root locus plot, because they are going to satisfy the magnitude criterion for some value of k. So it means making a root locus sketch will mean scanning the entire S plane for the points at which the angle criterion is satisfied, because once that particular sketch is available to you, in that particular case, that particular sketch becomes the root locus plot, because the magnitude criterion will definitely be satisfied for some value of k. Okay? So now, yes please.
But all points satisfy this magnitude condition would mean that you are taking different values of k.
Yes, k is, root locus plot simply means that k is a variable from 0 to infinity. You see this k, otherwise the plot will not come, otherwise it is a point. If you take k as a point, where is the question of plot? The word plot becomes meaningless, because for k a particular value, then these will give you only number of roots equal to the order of the system. So when we are talking of root locus branches, when you are talking of root locus plot, so naturally it means that the k is a variable from 0 to infinity. The I have restricted it to positive value. For any positive value from 0 to infinity, all the points for which the angle criterion is satisfied will become the points on the root locus plot for some value of k. Look at the sketch we had made for the pole 0 system: -1, -2, -5. Now you see that if you apply the angle criterion, I did not give you the method. If I apply the angle criterion on this, all the points on these things satisfy the angle criterion, on the red lines, and all other points do not satisfy the angle criterion. That is also important. The points on the red lines only satisfy the angle criterion, and all other points do not satisfy the angle criterion. Okay, and therefore I can say that all the points on these red lines are the root locus branches for some value of k, and the k, as I will give you the methods, k can be scanned this way: k is equal to 0 is here, and k is equal to infinity at this 0 branch. Now there was a question over here from him as to what is the center and the circle of this particular radius. Yes, this particular root locus plot. I leave this as an exercise to you. If GS HS, this is my last point, is equal to k S plus B over S plus A1 into S plus A2, okay, please see that it is a simple exercise for you. The root locus, this particular circle, has a radius equal to minus B0, okay, for you to prove this, and center, the center in this particular case is going to be B minus A1 into B minus A2 under the root. This is your center circle. I leave this as an exercise for you. Okay, minus B0 is the center and this is the radius. This is, since this is a simple one, we could obtain an analytical expression, but in general analytical expressions are not possible, and I am going to give you the root locus sketching method, how to sketch the root locus. And I conclude my discussion with the last statement, that I start with the angle criterion. Given an open loop transfer function, I scan the total S plane that satisfies the angle criterion, join all those points to get the root locus plot. Thank you.